Hello everyone, thank you for your interest in listening to this talk today. I'm Mohammed and today I'll present our work WhiteHaul. This work has been done with my collaborators Mortaza from University College London, Mahish and Peter from University of Edinburgh. As we speak today, there is around half of the world's population still doesn't have internet access. And there are several reasons behind that, but mostly it is an economic problem. Let me explain that in more details. First, the majority of population with no internet access live either in rural or low-income areas. These areas lack of affordable network infrastructure. Mainly, we are talking here about the backhaul network infrastructure, where all the traditional backhaul solutions are expensive. That high cost limit the service providers and mobile operators from extending their infrastructure to these regions. So let's take a look at the high-level view of the network deployment in rural areas. Here we have two kinds of network infrastructure, access and backhaul network infrastructure. Our focus here is on the backhaul network because it has a major contribution to the overall deployment cost. So as we said, the existing backhaul solutions such as the satellites, fiber links, and wireless microwave are too expensive to be rolled out in rural areas. So in this work, we ask ourselves a question of how to reduce the cost of backhaul network infrastructure, which in turn will play a significant role in enabling universal internet access. So to answer that question, we propose exploiting spectrum white spaces, where the key idea is to aggregate the unused spectrum portions, usually named as white spaces, to provide a low-cost, high-capacity backhaul system. In this work, we are focusing on TV white spaces. So briefly, TV white space spectrum is the unused spaces in UHF TV band, which in general range from 470 to 790 megahertz, with some differences from one country to another. So it's the orange color in that figure. So why TV white spaces? So actually there are several reasons for that. First, TV white space is kind of unlicensed spectrum with no spectrum license fee, which reduces the overall cost of TV white space backhaul solution. Second, TV white space is widely available in rural areas where there's a limited number of TV transmitters. Third, TV white space spectrum has excellent propagation characteristics. That means longer range and better penetration in non-line of sight environment. So when building such a system, we had different challenges that we had to address. The first of these is that TV white space channels are narrow. It can be either 6 or 8 megahertz depending on the regulation. So what is the implication of that? It's very simple. Narrow channel means limited capacity. Another challenge is that unlike Wi-Fi, TV white space channel exists in non-contiguous manner. So having one contiguous channel with a size of 160 megahertz is unlikely to exist in TV white space spectrum. So we confirmed that by using a real-world TV white space spectrum availability data that we collected from a commercial geolocation database for all rural regions in Scotland. And we found that in 50% of these rural regions, the TV white space spectrum is fragmented into 6 chunks. The second challenge is the high degree of diversity in TV white space. Let me explain the reasons behind that in more details. In TV white space, the device has to query a geolocation database to get a list of available channels and their corresponding transmit power. By available channels, I mean the list of channels that can be used by that device. In other words, the TV white space device is not allowed to use any random TV channel. However, the available channels change from one location to another. That change of TV white space available channels create diversity in terms of spectrum chunk size. This is a CDF figure for a percentage metric, where percentage here represent the ratio between the size of TV white space spectrum chunk to the total size of TV white space available spectrum. As we can observe on this figure, the size of the first largest chunk, the red curve one, varies significantly, where in some locations it represents only 20% of the total TV white space spectrum, and in some other location it represents 80%. We also observe a high degree of diversity in terms of transmit power levels, meaning that the allowed transmit power is not always the same, and it changes from one location to another, even for the same channel. For example, the allowed transmit power on TV white space channel number 1 can be 20 dBm in one location and 30 dBm in another location. This is a CDF figure that shows the transmit power differences for different point-to-point link distances when both endpoints using the same TV white space channels. We observed that the median power difference value between the link endpoint for 10 kilometers backhaul link is around 18 dB. That power asymmetry leads to different level of received signal strength at both endpoints, which accordingly means that the MCS values used for uplink traffic would be different than the MCS values used for a downlink traffic. In other words, the effective link capacity is different in uplink and downlink directions. That asymmetric nature is also observed in the traffic of the backhaul links, where the amount of downstream traffic is much higher than the upstream traffic. To confirm that, we collected traffic traces from Tigula network, which is a long-running rural community wireless access network. The one-week traffic traces shown in this figure is collected from the fiber backhaul link of this rural community network. In these traces, we observe a high degree of asymmetry, with the average daily downstream traffic around 63 GB, while the average daily upstream traffic is around 4 GB. Our key contribution here is WhiteHaul system, a hybrid cross-layer aggregation system for TV white space backhaul. This is the overview architecture of WhiteHaul system. It composed of hardware layer and a software layer. So in the hardware layer, we use a multi-radio architecture. Specifically, we combine multiple commodity Wi-Fi cards using a single antenna. The RF signal generated from these Wi-Fi cards are up converted to TV band signal frequencies using custom designed frequency conversion substrate. These hardware components need a software layer to orchestrate their operations. In the software layer, we leverage Multipath TCP at a link level tunneling technique, where we propose a new cross-layer congestion control algorithm that distribute the user traffic among the various TV white space spectrum chunk and enable efficient bandwidth utilization. We also propose an adaptive time allocation mechanism to handle the asymmetric characteristics of both link capacity and backhaul traffic. That combination of software and hardware layers is what represents WhiteHaul node. This is a typical deployment scenario for WhiteHaul system, where we have two WhiteHaul nodes. One is at the edge of the rural village, and the second one is close to the nearest internet point of presence. And also we have two kinds of channels. We have a set of data channels that carry the user traffic, and a single control channel that's used for coordination between two WhiteHaul nodes. So due to the time constraint in this talk, we will only focus on TV white space conversion substrate and the multipath TCP module, but please feel free to find details on the other component in the paper. So we start first by TV white space conversion substrate. So the conversion process can be realized using RF mixer and local oscillator. We then use a combiner splitter component to put multiple non-overlapping TV signals into one single antenna. So voltage-controlled oscillator are the most commonly used oscillators in the up-down conversion process. However, it has some key limitations in our context. First, it has a low tuning sensitivity with average tuning sensitivity of 10 MHz per volt. So voltage-controlled oscillator can be a very good solution for down conversion process if we have control over the input RF signal. Why? Because we would be able to compensate the lower sensitivity of voltage-controlled oscillator with a very fine-grained input RF signal. However, as we are restricted to the predefined Wi-Fi channel, using voltage-controlled oscillator with low tuning sensitivity can create improper null subcarrier alignment, as demonstrated in this figure. So this is a screenshot from a spectrum analyzer for a down-converted signal using 11 AC card and voltage-controlled oscillator. The target frequency here should be 610 MHz. However, as we observe in that figure, the null subcarrier component is not well aligned, and that would create a severe adjacent channel interference problem. Second, voltage-controlled oscillators produce unwanted emission, and that reduces the quality of the down-converted signal. In the same experiment, we observe SNR value of the down-converted signal was 5 dB less than the original RF signal. To overcome these limitations, we propose using SDR-based oscillators. A software-defined radio is used to generate a sinusoidal signal which acts as a local oscillator signal to the RF mixer. Using the SDR-based oscillator, we were able to achieve a very fine-grained oscillator signal with up to 1 kHz granularity, and that allows us to avoid any improper null subcarrier alignment. And also, due to the better quality of the oscillator signal, we get a down-converted signal with a high SNR value, similar to the SNR value observed on the original RF signal. So now we move to the multipath TCP algorithm that we designed for WhiteHaul system. In the multi-radio architecture, each radio can be seen as a single data channel. In order to bond these disjoint data channel into one single logical pipe, we need an aggregation mechanism at the software layer. The main function of that mechanism is to glue a set of heterogeneous data channel into one logical pipe by transparently distributing the user traffic among these channels according to some certain criteria. To achieve that objective, we propose using multipath TCP. So multipath TCP has a major advantages over all other approaches. First, it has a built-in mechanism for retransmission and reordering, which are very much required when the interfaces are heterogeneous, such as in our scenarios. Second, multipath TCP can be flexibly adapted to distribute the traffic across multiple interfaces. Let's take a look at the following example to clearly understand the multipath TCP function in WhiteHaul system. In WhiteHaul system, we have two nodes. One is located at the edge of the local community, and the second one is located closer to the internet point of presence. So multipath TCP is running only on these two nodes, and it's not running at the user equipment side. When the packet arrives from the local community, and multipath TCP encapsulated into multipath TCP header, forwarded over one interface, and then the packet is received on the other end, decapsulated by the multipath TCP module, and then forwarded over the internet. This process is reversed in the opposite direction. One of the key functions of multipath TCP is to distribute the traffic among the underlying interfaces. That traffic distribution is actually a function of each interface capacity and the minimum RTT observed on each interface. So the key message that we want to deliver here is that in order to fully utilize the underlying sublinks, multipath TCP should be able to estimate the capacity of these sublinks accurately. Multipath TCP relies on the congestion control algorithm to estimate the link capacity. However, in our settings, there are some key characteristics that are different than other environments where multipath TCP has been commonly used. First, in TV white space backhaul, there is no competing flows. That means there is no actual network congestion, and achieving network fairness between competing flows is not important. Second, the majority of packet drops in backhaul environment is due to the poor link quality problem, especially in non-line of sight environment. However, the existing multipath congestion control algorithm like Leia, Ulia, Cubic react poorly to packet losses. That makes the underlying link to be underutilized when packet drops are random and not due to the actual network condition. Also, these algorithms are slow and inaccurate in tracking the underlying link capacity when it fluctuates, which is very common in TV white space outdoor environment. This may result in extensive packet drops and inefficient link utilization. To solve this problem, we propose a new cross-layer congestion control algorithm for multipath TCP. So we start first by trying to solve the inaccurate tracking of link capacity. And to achieve that, we propose using explicit periodic feedback about the sublink capacity sent from the corresponding MAC layer to the multipath TCP module. We then use that information to estimate the optimal congestion window size for each sublink using bandwidth delay product. So knowing the sublink capacity allows the algorithm to quickly ramp up the sending rate. For the misleading packet drops, we try to maintain the sending rate close to sublink capacity. We achieve that by slowly shrinking the congestion window by only 10% in case of random packet losses. We also monitor the queuing delay of each sub-interface or sublink, so that if the lost packet leads to a congestion window size becomes smaller than the estimated BDB, we quickly ramp up the congestion window as long as the queuing delay is below a threshold. The key point here is that WhiteHaul ensures that each multipath TCP subflow always saturates its underlying capacity. We have implemented a prototype of WhiteHaul system and done similar experiments to test its performance in different scenarios. So let's have a look at the experimental setup first. So we have two Ubuntu 16 small form factor PCs running WhiteHaul software layer including the updated kernel implementation of Multipath TCP with our new congestion control. Then we have 6 MikroTik 11AC cards attached to these PCs with a gigabit Ethernet interfaces. We have 3 cards at each site. Then we have a WhiteHaul conversion substrate at both sides. At one side, we connected a client laptop, which acts as a client in the local community network, and we use it to generate a TCP traffic. The other WhiteHaul node is directly connected to the local server through gigabit Ethernet interface. So using that setup, we study the maximum TCP throughput that WhiteHaul link can achieve when using 3 contiguous and non-contiguous TV white space spectrum chunks and with different configuration. So we have on x-axis the MCS values configured for the 3 interfaces, and on the y-axis we have the throughput. WhiteHaul achieve maximum throughput close to 600 Mbps when it's configured to use 3 contiguous TV white space chunks with a total size of 240 megahertz. In the second experiment, we try to understand the efficiency of WhiteHaul conversion substrate. So as we down-up convert the 5 GHz signal to TV band signal, there might be some losses in that conversion process, and that could lead to bad performance or affect the performance. So to study the conversion efficiency, we propose a percentage metric as the ratio between the throughput achieved on TV white space after the conversion process to the throughput achieved on the 5 GHz band in the same setup but with no conversion. And we found that in all different configuration and different MCS values, the conversion substrate achieve efficiency between 96 to 99%. There was only one case where the conversion efficiency slightly dropped to 89%, which is when having a configuration of 3 large contiguous chunks, each with size of 80 megahertz. The main reason for that drop is due to the limited interchannel separation between these chunks, and that creates adjacent channel interference problem. That adjacent channel interference problem can be alleviated by using or by having a sufficient separation between different chunks. In the third experiment, we try to understand the performance of WhiteHaul multipath TCP congestion control in different conditions and in the presence of packet loss. So we did an experiment with 2 interfaces. Each interface has a different characteristics in terms of packet loss and capacity. And then these configurations are emulated using LinuxNetM. So in the following figure, we have on x-axis the configuration of the first interface. On the y-axis, we have the configuration of the second interface. And we draw a heat map for the ratio between the aggregate throughput achieved when using these configuration to the aggregate throughput achieved when using the same capacity configuration but with no packet loss. So for that scale, 1 means ideal scenario, where the throughput achieved in the case of losses is similar to the throughput achieved in the case of no losses. So these are the 2 heat maps for cubic and WhiteHaul congestion control. We observe that WhiteHaul achieve a superior performance compared to cubic in all scenarios. Even in some scenarios, WhiteHaul achieve an order of magnitude better performance than cubic, thanks to the periodic feedback from the lower layers that helps keep track of the optimal congestion window size and allow quick ramp up to the sending rate in case of random packet drops. So after we saw all these performance gain, the question now is how much it costs to have such a system. This table provides a brief comparison between the cost of WhiteHaul system under different configuration compared to the commercial TV white space backhaul solution. So the cost of WhiteHaul system is a function of amount of spectrum it can utilize. The detailed breakdown of that cost analysis can be found in the paper. But in general, WhiteHaul costs slightly lower than the state of the art, while it can aggregate an order of magnitude more spectrum and achieve capacity of 9 times more than the state of the art. Our future work will focus on real-world trials of WhiteHaul, as well as examining its wider applicability beyond TV white space spectrum. So I will conclude my talk with this summary slide. Thank you for your attention, and I'm very happy to take your questions. Thank you.